Hi, it's great to have you here. Today we're looking at combination sum. Let's break this problem down in a way that makes sense. Now, this problem is a foundational problem for backtracking as it introduces a technique which is useful for many other backtracking questions. The problem statement given to us here is that we are given an array of distinct integers, candidates, so something like that, and we are also given a target integer, 7, for example. We have to return a list of all unique combinations of candidates where the chosen numbers sum to the target. So we have to return all unique combinations of the candidates. For example, the combination that we got is 2, 2, 3. So it used 2 twice and then a 3, which sums up to 7. Further, problem statement says that the you may return the combinations in any order. So we can return the answer in any order. The same number may be chosen unlimited number of times. We've already seen that. We used 2 twice to get the sum 7. And then the two combinations are unique if the frequency of at least one of the chosen numbers is different. This is just to say that we cannot choose a combination where it has the same elements. So that's just a fancy way of saying that. It further says that the test case are generated such that the number of unique combinations which sum up to the target is less than 150. So the worst test case that is given to us, it'll have less than 150 combinations. Let's start breaking this down with the race framework. Let's start with reasoning. Reasoning is the first stage in our race framework. Race framework is a framework which is really nice to organize these kind of questions. I'll link a detailed video in the description. So under reason, we essentially reason with the question. We'll reread the problem statement if we need to. Let's continue reasoning and quickly note down two observations about this question. The first observation is very obvious. We have to generate all combinations. So we'll need a technique to generate all combinations. So let's quickly write that down. The second observation is also very straightforward. We'll just note that we can use each candidate unlimited number of times. With that, let's start looking at our approach and let's start looking at the technique to generate all combinations. So now we're looking at the approach section. Approach is the A of the race framework. So let's look at the technique to generate combinations. Now this is a very fundamental technique. Given our example 2367, so that's a list or the candidate that's given to us. What we do that at each stage we decide either to use the first element, in this case it's 2. So either we use the first element or we do not use the first element, and that's precisely the choice we'll make at each node. You keep making that choice and eventually at the leaf you will start creating combinations where each candidate can be used unlimited number of times. Let's see how that goes. So here at this node, when you use 2, you are essentially saying that on the left of this tree you will have combinations where the prefix will always be 2. So the prefix of the list of the combinations that you generate will always be 2, and on the right it will be empty. But for now, in the subsequent stages, we'll consider other elements. So here on the left, when you consider 2, we pass 2, 3, 6, 7 as it is, and on the right we'll pass 3, 6, and 7. So by that, you ensure that on the left, you always have 2 in the candidates of the combinations you generate, and on the right, you won't have that. Okay, with that, let's continue building the left side of the tree. The right will follow the same pattern. So on the left, we keep making the same decisions. On the left here again, we'll pass 2, 3, 6, 7, and we'll include 2 in our candidates. And here we will not include 2 in our candidates, and we'll pass 3, 6, 7. All right. Again, on the left, we'll do the same thing. Let's look at on this side of the tree so that I can show you how the second element gets considered. So it gets considered in a very similar way. On the left, we'll add 3 and pass 3, 6, and 7. On the right, we don't pass 3. And the candidates that we pass is 6 and 7. On the left here, we make the same choice. We say 2, 2, and we'll have another 2 here and pass 2, 3, 6, 7. Okay, and on the right we'll do the same thing. We don't consider 2 here, so this remain as it is. But now notice here we passed 3, 6, and 7. So in the left side of this part of the tree we'll add 3, so 2, 2, and 3, and on the right we do not add 3, but we'll pass 6 and 7, and here we'll pass 3, 6, and 7. This right here becomes our one of the solutions. But if you notice this tree, because we want to focus on the technique of generating these combinations, if you focus on this tree now, you'll see that on the left, wherever we consider 2, all the candidates that we generate in the subtree will always have 2 in the prefix. And that's true for each of these subtrees. So here, if it's 2, 2, you'll always have 2, 2 in the prefix of all the combinations that you generate, right? Similarly, when you have 3, 6, 7, and you go on to the right, if you start with 2, 3, everyone, all the candidates that get generated in this subtree will always have 2 and 3 in the prefix. That is one very important observation about this and learning about this technique. The second learning that you can take away from this tree is focusing on what we pass on each call. So every time when you go on the left, where you consider the first element, which is 2 here, you pass that 2, 3, 6, 7, including 2, onto the left, and then remove that first element to the right. You do that everywhere. And that is how you'll start generating the cases where you will be able to, one, use the candidates unlimited number of times. That's what the question said. So here, if you keep going on the left, you'll keep using 2 more and more number of times. And also, if you like want to miss 3 and just use the consider the case of 2, 6, and 7, you can do that as well. So on this part of the tree, if you see, we passed out 6 and 7. So every element on the left here, where you have 6 and 7, you will add 6. So you will have 2 and 6 now in the candidate prefix. And on the right, you will not have that. But interesting thing about 2 and 6 is that we were successfully able to skip 3 completely here. So with the technique clear of creating combinations, we just need to satisfy one more condition, which is that we want to make sure that these combinations sum up to the target. And that's very easy. Like whenever you create a combination, you just sum them up. So here, 2 plus 2 plus 3 plus 2 plus 2 plus 3, 7. You and define that as a terminal case. So whenever your sum becomes equal to, that becomes a terminal case. If it becomes greater than, that also becomes a terminal case. So if your sum becomes greater than the target, that also becomes your terminal case. And another thing is, like, you will have some nodes on the tree where you will not have any more candidates. So if your candidates in your subsequent calls, if the length of your candidates that you want to use in your subtree, if they become equal to 0, that also becomes your terminal condition. So the thing to notice here is that this combination generation technique, this remains the same. We just need to adjust to the constraints that the question gave us. So here you have to sum up to a target number and define your terminal conditions. Use this pattern and you'll be able to solve many more questions where the technique will remain the same and you just need to come up with the terminal cases. Let's look at the code to make that all very, very clear. So no surprise here, exactly what we discussed. Let's start with some bookkeeping. So we will, as usual, define an answer variable. So this is the variable which will collect all our answers. And then let's create a recursion function. Self target, because we'll need target, candidates, and our current. So this is the variable which will hold our intermediary results, right? We'll make 2 calls, self.recursion. In the first one, we will subtract. So this is what it means that we will use the 0th element here, so, and which means that we subtract it from the target. So the way we'll track it is we'll just check if our target goes to 0, and that's equivalent to that the candidate summing up to the target. So if that happens, then we just we take our answer variable and append the solution here. So we'll append current here, right? And don't forget to return. We return from here, right? So here the first thing is target, then we use candidates. So wherever we use the 0th element, we include and pass the element. So in our example, we had 2. So we subtracted 2 from our target, and then we pass the entire array of 2, 3, 6, 7 in our target, right? And since we are using it, we have to record our intermediary result. So current becomes current plus candidate 0. We'll make a similar call here. The difference is we'll not use the 0th element, which means that the target remains as is. We don't subtract. We don't add it here. The difference is that we exclude it from the candidates that we send to our further calls. So this is our left subtree and this is our right subtree. So this will create our recursion tree. But we discussed about 3 of our terminal conditions. One, where the target becomes 0, which is that all the candidates sum up to the target. Another is if your candidates, if the length of the candidates, if that becomes 0, that is also when you return. So you just return none because we are capturing the answer in a global variable, which is fine. You just return none. Another situation is that when your target becomes less than 0. So if your target becomes less than 0, you keep subtracting, and if it becomes less than 0, that is another uh, cue for us to return. Let's just quickly review if we need to adjust the order. So here the target is 0, which means that this will not conflict. In case the candidate is 0, these are completely independent. Yeah, so this, we can have these in any order. I don't think it'll be a problem. With that, we just have to call our recursion function from our combination sum. So we'll just do that. Say self dot, remove this self, target is target, candidates and candidates. This will be an empty list, right? And at the end, we return self dot answer. And that should be okay because we need to return a list of list, which is a list of ints. So that looks fine. All right, we can try that a run and let's see if that works. Okay, that seems to work. Let's just quickly look at our test cases. This is fine. And okay, we have a test case where the answer is not available. And in that case, it does return an empty array. All good. Okay, so let's submit that and see if that works. All right, looks like that works. That's all good. Perfect. So let's quickly review that together. It's exactly what we discussed in the approach section. You make two calls, one to the left, another to the right. The one you make to the left, there you use the 0th element. So you use 2, which means that you subtract 2 from your target, pass your candidates as is. That means 2 included needs to be passed into the next stage. And you add that into your intermediary result so that it can finally be registered when you find the answer. That is when the target becomes 0. Right is also very similar. You don't include the 0th element, so target is as is. It doesn't subtract anything. However, you exclude 2 from the candidates that you pass onto the next stage. So onto the right, you don't add 2 anymore. So here, all you pass is 3, 6, 7 from our running example. Okay, and current becomes it remains as is because we are not using anything. So current is passed as is. All right, perfect. So now with that, I want to show you one more thing here. So here, if you see, we are retaining the list in every state, and that's a lot of memory that you use. So and I want to just quickly show you a solution where you can completely avoid this. So what exactly we need to avoid is that we don't want current to be added to each intermediary state because that's a lot of memory. So the classic backtracking technique is that you use or you maintain a global variable current. So instead of appending current here, we add the element globally. So we say candidates of 0. So that's what we were doing here. The only difference is here we were adding it for the next stage, but here we are adding it uh, like for the method in this function or the method call, which means that if you add it here globally for the function, you'll also have to pop that out. So this, I wanted to show you this because this is what becomes the heart of backtracking, where you use the variable to add and then remove it as required by the question. So this becomes sort of very important. I think that's the only small change that you need to do to adjust to this new technique or the new small trick to actually make it a backtracking solution. So if you run that, okay, we got wrong answer. Let's see, what did we do wrong here? So it looks like we append it and then we pass it and then we pop -1. Okay, what we need to make sure here is that you're appending it, you're appending the like the method global variable. So here you cannot do that anymore because your current will change, right? When you're passing it between your function calls for the call stack, your current will change. So here, when you append it to the answer, you actually need to make a copy and retain the copy. Otherwise, it's going to go change in the subsequent calls. And if it only appends the reference, that will become a problem because it will get changed, right? Okay, now if you run that, that should work. Okay, that works. Let's quickly submit that. Okay, all right, that also works. So I hope that was clear. And that's it for the coding section. Let's now move back to our writing pad. Let's quickly look at the evaluate after done with the code. So let's start with marking code as done. So our code is done. Let's look at the evaluate. For the evaluate section, the time complexity will be O 2 to the power n, where n is the length of candidates. And it's 2 to the power n because for each element we are making two choices, whether to include it or not include it. That's the easy way of saying it. You can actually interpret it as n over s, where s is the smallest candidate, and this is because the utmost you will go deep will be n over s, but this is a more complicated way, and I think this is perfectly acceptable. Space complexity will be O, uh, and it'll scale linearly with n, where again n is the length of candidates. Space is O of n, and that's it. The combination sum problem, like we started out commenting on, is a fundamental problem. It's very important that you do this question before you start out with backtracking questions. It gives you the technique to generate combinations, avoiding duplicates, uh, and therefore it is useful in many other backtracking questions wherever you need to generate combinations. So I hope I was able to explain this clearly. Thank you so much for watching, and see you in the next one.